Okay, Bohr's model of the atom. We have n equals 1, n equals 2, n equals 3, n equals 4. That's 1, 2, 3, and 4, little n. And those are the principal energy levels or shells. And electrons are going to reside as close to the nucleus as possible, but these things fill up. 1 can only actually hold 2 electrons, 2 can only hold around 8. Not around, it can hold 8. So we're going to look at where those electrons are going to be in their ground state. Okay, so each energy level is labeled 1 through whatever, like I just did. Now each energy level has that many sublevels. So 1 has 1. It's called the S sublevel. Once you get to n equals 2, though, that has 2 sublevels called S and P. Now if you recall, looking at those probability maps, S has 1 orbital, it's a sphere. P has 3 orbitals, they look like dumbbells. Now, 1 doesn't have that. 1 just has the S, the sphere, 1 orbital. But once you get to level 3, n equals 3, we're talking about 3 sublevels, S, P, and D. And if you recall, S is the sphere, P has 3 orbitals shaped like dumbbells, and D has 5 shaped like clovers. If you get to n equals 4, you have 4 sublevels, S, P, D, and F, 1 orbital, 3 orbitals, 5 orbitals, and 7 orbitals. Now, that's the trend, 1, 3, 5, and 7. Now, those are orbitals. Each orbital, no matter what kind of orbital it is, it could be a sphere, it could be dumbbells, like the P has, it could be little clovers. F sublevel has 7 orbitals, following the trend. If you ever get to G, it had 9. We run out of elements. Orbitals, they look a little bit like flowers, actually, a little bit like daisies. We don't have pictures of those in the book, but those are mathematically defined areas of high probability. Always just keep that in mind. 2 electrons per orbital. I don't care what kind of orbital it is, 2 electrons per orbital, Pauli exclusion principle. They do have to have opposite spins. Okay, so recap. For n equals 1, that has an S sublevel, 1 orbital, 2 electrons, because of the 1 orbital. N equals 2 has an S and a P. S can hold 2 because of the 1 orbital. P can hold 6 because it has 3 orbitals, those little dumbbells. Once you get to n equals 3, you have an S, a P, and a D. S can hold 2, P can hold 6, D can hold 10 because of its 5 orbitals. And so on. F could hold 14, right? 7 orbitals. Okay, another recap there. All right, for electron configurations, here's what happens. Now, it doesn't do a superscript, unfortunately, so I'm going to redo it. Hydrogen is 1s1. Now, this one right here, the 1, represents the principal energy level, n equals 1. S, or this one right here, could be a P or D or an F, that represents the sublevel, and this is the number of electrons. Now, S can actually hold 2, but hydrogen only has 1. And you should follow along on the periodic table as I talk about this and go through this. Hydrogen has 1, so we only need room for 1, and there it is. Now once you get to helium, helium's electron configuration is 1s2. First energy level, S sublevel, it can hold 2, and helium has 2. Bam, there you go. Lithium has 3. It's going to be 1s2. Now, 1 is full. Energy level 1 is done. It only had an S. It can hold 2. It's done. We got to go to the second energy level, go to its S. Now, it can hold 2, but we only need it to hold 1 more, a total of 3 electrons. Lithium is 3. Beryllium is 4. So we would go, beryllium would be 1s2, 2s2, that's 4. Boron would be 1s2, 2s2. Now, the S is full, but the second also has a P that can hold 6, and we only need it to hold 1. So boron's electron configuration is 1s2, 2s2, 2p1. Now, as we continue, carbon is 6, so it'll be 1s2, 2s2, 2p2. I need 6. Now, P can hold 6. If you go on to neon, neon is atomic number 10. We have to find a spot for 10 electrons. And so 1s2, 2s2, 2p6. And P can hold 6, and we need it to hold 6, and so that's its electron configuration. Okay, as we go on, magnesium has 12 that we've got to find for. So 1s2, 2s2, 2p6. Now that's 10, but we need 12. Now, how many or well, energy level 2 is full. Its S is full, its P is full, so now we're going to have to go on to energy level 3. And there's an S, and we need 2 more, and S will fit 2 more, so I think we're good. All right, aluminum, 1s2, 2s2, 2p6, 3s2. We need a place for one more because aluminum has 13. And so the S is filled, but 3 also has a P. It also has a D, so we'll consider that. I only need one more to go in there, so it's going to be 3s2, 3p1. That will be aluminums. Now, if you look at argon, argon is 18, so the electron configuration here is going to be 3p6. Now, if you'll notice, 3 is, energy level 3 has its S filled, its P filled, but it doesn't have its D filled, so we can still fit more into D. So, let's take a look what we would do next. Now, energy level 4 actually gets filled up sooner, 4s gets filled up sooner than does 3D. So it's one of those weird little things where 4s dips closer to the nucleus than 3D does. So it's a little weird. I'll show you a way you can keep track of it. So taking a look at potassium, what you have here is an electron configuration that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So before the 3D gets done, we actually go to the 4s. Now this probably past the 4s, the electrons start filling to the 3D, then they go back to the 4p. So let's skip vanadium right now. There's actually an easier way, and what you want to do is to look at hydrogen, and on the periodic table that I gave you, which is really important to use that one, follow along with me. Hydrogen, think of helium over here, is 1s. Now notice that S has 2 electrons. It can hold 2 electrons, and that block right there has 2 columns. And you'll see 1s, 2s, 3s, 4s, 5s, 6s, 7s. Now, after that, you come over to boron, and notice it has a little 2p in front of it. That's your p block. Now, p's can hold 6 electrons. We'll count how many columns. 1, 2, 3, 4, 5, 6. 6 columns, and that's your p block. So this table was put together by Mendeleev, 200 years ago. Quantum mechanics came along 100 years later, perfectly predicted exactly what Mendeleev had said. So once you get done with 2p, go to 2p6, that's neon, come to 3s, and get to magnesium, that's 3s2. Come on over to aluminum, you're getting to 3p. Go all the way to argon, you're going to 3p6. Now, follow it back around to potassium, you're at 4s, calcium 4s2. Notice now you go back to 3d. Now that you filled up the 4s2, you go to 3d. Now you're at scandium, you're going to go 3d all the way down to zinc, which would be 3d10. So notice the D block has 10 columns, but how many electrons can a D sublevel hold? It can hold 10. 5 orbitals, 10 electrons. So now we're at 3d10. Notice what happens right before gallium. We pop back up to 4p. So we had 4s2 here, 3d10. We're going to go back to 4p at gallium. 4p 1, 2, 3, 4, 5, 6. Now at krypton, we're at 4p6. Swinging around here, we're back to rubidium, 5s2 to strontium. And then we're going to go back to 4d. Yttrium will be 4d. All the way through cadmium, 4d10. And we're going to go 1, 2, 3, 4, 5. We're going to go to 5p. Indium will be 5p. 5p6, we're at xenon. Swing back around, we're at 6s1 for cesium and 6s2 for barium. Now, something interesting happens. I want you to make a note of this. Right before lanthanum, you'll notice that 57 through 70 is taken out of the table. And it's taken out of the table because it would otherwise make the table very long and thin. It wouldn't fit on a page nicely like it does. So just don't forget them. But before we go to lanthanum, what's going to happen is we're going to go down and it's going to be 4F. So the lanthanide series is 4F. Notice that F's have 7 orbitals, hold 14 electrons, and you'll count across here, you'll see there are 14 columns. It's perfect. Now, when you get to the end of the lanthanide series, you pop back up here, okay, and now we're going to be at 5D. And we're going to count across. 5D to mercury would be 5D10, okay, and then we're going to go to 6P. And we're going to go to 6P6 would be radon, 7S2. Now, there's the actinide series that got taken out of the table, okay, and we have the actinide series, which would be 5F14. Pop back up here, you're talking about 6D, 6D10, and then you go to 7P, and then we kind of run out of electrons. Okay, now you need that table and you need to follow. So there's another way to do that. It's called the Aufbau principle. We don't talk a lot about that because you can just follow the table. All right, there is a shortcut method, and the shortcut method is this, because these things get a little long. Find platinum, it's number 78, count backwards to the previous noble gas, and that is xenon. So what we're going to do is we're going to put xenon. Now beyond xenon, writing that like that, is like you're basically saying you've gone all the way through 2P, 3P, 4P, 5P, 5P, 5P6. It's like you've written everything through 5P6. But now you got to go on. And so I'm going to write 6S2. I'm going to remember that 4F14 got taken out of the table. I'll pop back up here. And now we're in the 5D block, and we have to go 8 in to get to platinum. So that's platinum's electron configuration. Polonium, if you take a look, is number 84. You actually have to go even further. You have to go 4 into the 6P block. So it'll be the same thing here. Don't forget that at 4F14, 5D10, 6P4. Okay, there are some exceptions to the rule. Copper, for instance, silver, gold, all the precious metals, kind of interesting, does this. Now find copper on the table, but copper should be argon 4s2 3d9, but instead it only puts 1 in the 4s and actually fills up the 3d. So there's just some exceptions. A lot of the lanthanide and actinide series do that too. About half of them follow the rule, half of them don't. Okay, there's some orbital diagrams too. I'm going to go quickly through. 2 electrons per orbital, opposite spins. That's the Pauli exclusion principle. They will also spread out in the PDF orbitals because the electrons just don't want really to be with each other if they can help it. They're both negative. This is called Hund's. Okay, so how we would do the orbital diagrams is this. Hydrogen is 1s1. We would draw a little box to represent the orbital, and we put a little spin arrow up, half arrow. Helium would be helium would be 1s2. We go 1 up and 1 down. If we look at nitrogen, nitrogen's electron configuration is 1s2, 2s2, 2p3. We draw that by drawing 1 orbital here, 2 electrons, opposite spins. 2 here. Now p's are 3 orbitals, so we're going to draw 3 boxes, and according to Hund's rule, those are going to spread out, 3 in each. All right, I'm going to go all the way to vanadium, and vanadium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. All right, so that would be that orbital. That one, I would draw 3 boxes here. 1, 2, 3, 4, 5, 6. I'm just drawing them like they'd fill up. 3s2, 1 up, 1 down. 3p6, draw 3 boxes. Up, 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 down, down, down. 4s2. 3d, I'm going to draw 5 boxes because, of course, 5 orbitals in the d, and there's 3 of them. 1, 2, 3.